Everyone, it's 5:35. Pass it over to Gian to get started.
Amazing. I'll start turning on my video. Awesome. Hey guys, thanks for coming to collaboration between Fintech Society and Data Society. Today we're going to go through a workshop on neural networks in the context of predicting Bitcoin and cryptocurrency. So my name is John. I am the Education Director of Fintech Society. I'm here with Julian, Noah, and Sophie to discuss more on this workshop. So without further ado, let's get started. Let's start with the context of this workshop. As we know, there are different kind of assets out there. So the traditional assets we have, such as stocks, properties, and we have some new asset classes such as ETFs and cryptocurrency. And there are many ways on how do we make investment decisions for this. There are like fundamental analysis where we can look on the PE ratio, for example. And there are some analysis we call technical analysis, where we just do some prediction based on the prices in the past. And in this context, we will go through the technical analysis using price prediction. And the reason for that is because cryptocurrency is one of the most turbulent asset classes, and it makes more sense to figure out the direction of the prices based on past data. And using crypto price prediction, it can help multiple stakeholders to steer towards the right way. So for investors, definitely they would want to know whether or not it is the right investment decision. And for financial researchers, it might be useful for them to observe the patterns of currency movement and make some legislation in the future based on those data that they have received. Now, before we jump into the prediction itself, there are some concepts we should discuss. First of all, it would be time series. So in a nutshell, time series is a sequence of observations or data points collected in constant time intervals, whether that be in daily, monthly, or yearly. And time series involves creating some assumptions or interpretation about the sequence. So if you see like the picture at the bottom right, that's like the graph of Dogecoin. You can make an interpretation such as Dogecoin trend seems to be downhill. And there are some assumptions that can be made as well in the context of time series, such as having no outliers. So based on that, it means that you're going to take away any outliers from your data. Now, the key components in a time series, it will be having one variable across a time. So with the example of Dogecoin, it would be like, what is the price of Dogecoin for a trend of 1 year? And then during in time series, we will be focusing on some patterns based on the time. It would be trend or seasonal or even cyclic components. Now, time series forecasting makes use of the best fitting model, essential to predicting the future observation. So we will there are different kind of models out there, and it's on our discretion on choosing what models that we will be using. And this will be based definitely on processing current and previous data. Now, this is like the framework on the time series forecasting process. There are 6 main steps. Firstly is to understand what's your goal definition. So whether or not it's to figure out when's the best time to enter cryptocurrency, or just figuring out when cryptocurrency is going to crash on a particular month. That might be your goal definition. That it must be made before we start the time series forecasting. And once you know what you want to achieve, the next step would be gathering the data and and preparing the data itself. To gather the data, there are multiple sources such as Kaggle or Yahoo Finance. And once you get that data, you can start preparing them depending on the time series. So whether or not you want to make the observation to be daily or weekly. And once that's being prepared, you can start doing some data analysis from that data. So assumptions can be made here. So for example, you realize that there are some outliers, then you can do additional preparation and return to the previous step before coming to the next step, which is applying a time series forecasting method through the modeling. So you apply a model towards the data that you have prepared. And once we feel that the model has been great, we can start deploying them in a form of dashboards or report or web app. And at this last step, it would be evaluating and validating whether or not the model is good enough for the performance, comparing it with the real price data. Now let's some advantages of using time series. Definitely, it would be to understand underlying causes of trends and systemic patterns over time. So, for example, if you see the previous 2 years in May 2021 and 2022, there has been a crypto crash. Now, whether or not that crypto crash might be a cyclical thing or is it systemic, that is one thing that we can figure out from time series. And obviously, one of the main goal of time series, which is to predict future price changes, which everyone would love to figure out, and also highlighting seasonality and cyclical behavior in the data. Those are the advantages. Now, some of the disadvantages include lack of historical and seasonality data. So what it means is if your data does not have if you don't have any historical data, then we can't do any time series to the model because the model relies on a previous set of data. And secondly, which is usually the most the biggest disadvantage, is identifying the correct model to accurately showcase the result. This is pretty much what professionals are doing, figuring out what models will fit in with the data that you have. So we can't even tell you right now what's the best model to use, but there are some tools to figure that out, and it's based on your discretion and analysis to figure out what is the best modeling for that. And for the third disadvantage, it would be difficulty in obtaining appropriate measures. So for example, whether or not it should be modeled based on daily time or weekly time, those are one of the explorations that industry professionals will be going through with this time series forecasting. Now let's get into the model that we will be using, which is neural network. Now we need to understand what a neural network is. Neural network is just a form of machine learning. It is a series of algorithms which mimics the way that human brain operates. So you know how we analyze relationships, and pretty much what neural network does, it's just that algorithm which mimics our brain to do the same thing. And the goal of neural network is to teach computer how to learn from data to make prediction. Now, the word recurrent means that the information using this tool will go through a cycle. So when the recurrent neural network is making a decision, it will consider the current input and what it has learned previously from the previous cycles. And since it learns from previous data, it works very well for sequential data such as time series, financial data, and even with text, videos, and more. Now, an extension for neural network. This is just like a picture of how neural network will work. So we have the input, and all of the calculations will be done in the hidden layer. There are some recurrence happening there to go with the output. So an example for this is say a case where we want to figure out what a chef will cook based on the weather. So the input would be the weather, it's sunny or it's raining, and then the output would be the foods that the chef cooks. That's a very simple example of the recurrent neural network case. And now there's an extension called long short-term memory network. And this is what we will be using to predict crypto price. Instead of the normal recurrent neural network, you can see the picture at the bottom. We won't be getting into it as deeply as possible. I'm not even a master on this as well, but just think of it as Lstm is a more complex recurrent neural network, and it has more benefits compared to the vanilla RNN. Basically, what it does, it can store past information and forget any information that is not relevant. So yeah, this is what I've just previously discussed. With vanilla RNN, recurrent neural network, doesn't really put importance to the earlier input. So it will put more importance for the inputs that comes after at the earliest one we have. So an example would be if we see the Bitcoin graph at the right, maybe the ones, the recent data from 2021 would have more importance compared to those like in the previous years when Bitcoin has just started in 2016 or so. And LSTM tries to prevent that by having like a gate mechanism. So instead of just continuously adding data point and putting more importance towards the newer data, it chooses to forget some irrelevant information and adds more useful one to the long-term memory. And the advantage of using LSTM would be it's more computationally efficient, and it preserve and regulate information with gates. This is just like how the gate in LSTM work. There's an input gate, forget gate, and an output gate. But in a nutshell of what I've just discussed, these information are just the concepts of LSTM and recurrent neural network and time series. When we start creating the model, these will be pretty much handled by the library that we will be using, which is TensorFlow. And that comes into the general steps in building the model, which we will be going into. So firstly, we would need a real-time cryptocurrency data, and that would be through Yahoo Finance API. We will get some of the data there, but what important data we will be taking is the close price of the target crypto. And then we will be pre-processing this data using a library called Pandas and skTime. And then the main library that we will be using for the LSTM model is called TensorFlow. And it's an open source software library for machine learning and artificial intelligence in Python. Basically, industry professionals will be using TensorFlow a lot. So without further ado, let's get into the practical demo, building the model with TensorFlow. I'll hand this to Julian.
Hi. Thank you, Jian. Hi, I'm Julian Songkyun Yu, second year stats math student. I'm going to explain the basic part of our cryptocurrency price model, prediction model. So let's get into it. Like Jian said, we're going to use the price history from Yahoo Finance to let the machine learn the data. So let's install Yahoo Finance. And skTime is used for machine learning with time series. And to build the prediction model, we need packages from TensorFlow. And the following, and the following packages are for data visualization, like Seaborn, and Pandas for manipulation. So let's get the Bitcoin price history from Yahoo Finance, and let's check this data with using dot-head method. We can see there are opening, closing, high, and low prices. Since this data is based on the time flow, we better check this with a graph. To analyze data, it is important to divide some section to look into deep. So we can use dot-log method. This graph is showing the closing price after 9th of January 2022, and now we need to split the data set to train the model and use the model to test the set to the test set. We will train the model with the data until 1st of January 2022, which is, you can see that the data set on the left of the red line, and we will use the leftover 10% of data to test the model. And you can see the test by putting 0.1 on the test size. Let's plot and see the data we're going to use. It looks like this. And also the test data that we're going to test. And also scale the data with a formula, our data minus mean divided by standard deviation. The reason why we are doing this is to allow gradient descent to converge faster, which means that by scaling, the inputs are going to process faster and more stable. And here's the process of scaling it. And I'm going to hand the next section over to Nova.
Awesome. Very nice. So yeah, so I guess just to sort of recap what happened there, we loaded in the data, created some plots. This is the data that we're going to train the model on. This is the data that we're going to evaluate it on. One immediate problem is that you can clearly see that the shape of the training data and the shape of the testing data is clearly different. So we might run into issues later on there, but just something to keep in mind. So now we're actually going to build our model, and to do this, right, we have got a series of closing prices for Bitcoin, and that's just a single variable. So we ultimately want to convert this into a problem in which we can just feed it into TensorFlow and make some nice predictions. To do that, we're going to run this function called create sequences. Let's not worry about the code for now. We'll get into exactly what it does later. But if you consult this picture, you'll see how what's happening here is matching what is about to happen when I run this code. So we have this create sequences function, and what it does is it takes our series of Bitcoin closing prices, and what it essentially does is as follows. So if you look here, here's our training data, but it's been scaled, as Julian said. So just to recap, we aren't actually dealing with the actual Bitcoin prices, we're dealing with the scaled Bitcoin prices. And the reason why is because, these machine learning algorithms, they're trained using something called gradient descent. And it turns out the gradient descent algorithm actually does its job faster when the data is scaled. So here's the scaled data. And what we're essentially going to do is we're going to use these first 5 values to then predict the 6th one. So that's sort of what you're seeing here. So we're going to use these first 5 values, which I've highlighted, which also corresponds to this first row. And we're going to use those first 5 to predict the 6th one. So the one ending in 956, the one ending in 956. Then we're going to use these 5. So we're going to slide it down 1. So we're going to use these 5 to predict the 6th one, which is, 1074. And that's, the 1074 there. Then what we're going to do is use the next 5. And what that's going to do is help us predict the one after, so the 6th, ending in 988, ending in 988. So that's what this create sequences function does. We've programmed a sequence size of 5, and that's just sort of what I've explained there, using the 5 values to then predict the next one, which is the 6th. And you can change the sequence size, and that will, of course, change the dimension of this array. But ultimately, just think about it as using 5 values to predict the 6th, then using the next 5 to predict the next, and so on. And for this reason, we're actually able to split our data into training and testing sets, despite only having one series of Bitcoin closing prices. Okay. Now, it turns out when actually passing this model into TensorFlow, it does require a 3D array structure. What we currently have is a 2D array with our training data. And it turns out that once you feed it into TensorFlow as a 3D array, the neural network can, run the model and make the predictions and things like that. So if you're familiar with pandas, all we're really doing here is we're just really reshaping the array where the first dimension is the number of rows in the training set. Samples, we program a lot of these. The array is going to get passed into our model. Okay. So we're actually going to build the model now. And as Gian sort of alluded to earlier, sure, we can use RNNs, recurrent neural networks. They are relatively decent for, sequence related data, whether that's time series or predicting like the next word in a sentence if you give it like all the previous words. So like NLP sort of stuff. But the problem with RNNs, well, at least for this case, a lot of the time we encounter something called the vanishing gradient problem. And with recurrent neural networks, we have this thing called the vanishing gradient problem, and we won't go into the mathematics behind it. But essentially what happens is sometimes due to the gradients that get computed when actually training this neural network, like behind the scenes, sometimes our gradients can get smaller and smaller and smaller such that it actually stops the neural network from like further training. And now I won't get into the mathematics of how this thing called an LSTM cell can actually deal with that vanishing gradient problem. But what I will mention is that we are using an LSTM cell we are using LSTM, the concept of LSTM, to combat this idea of this vanishing gradient problem. But essentially, without going into the maths, you can see like a little extract I posted here. But by introducing LSTMs, we can actually like fight this vanishing gradient problem that like plagues all of like recurrent neural network modeling. So just a little thing to note there before we actually, call it over here. Cool. So we're actually building this model. We use TensorFlow, just importing it as TF. I know we imported it earlier, but just a reminder that we're using TensorFlow. I've set the seed to 1, and what this is just going to do is every time I rerun this notebook, or every time you rerun this notebook, you're going to get the same output, so just more reliable. Yeah, and now you're going to see this everywhere with TensorFlow models. But if you haven't used TensorFlow before, just see this as an introduction. Essentially, we're going to build a sequential model, sort of as Gian alluded to earlier, and we're going to add the special thing called the LSTM layer. Now, if you're wondering what these are just some parameters that come from the default implementation. If you don't come from a neural network sort of machine learning background, don't worry about it. But this is what's happening behind the scenes by default. I've just put it in there in case you were wondering. And if you notice here with this input shape, we're only modeling closing prices. So, it's the one there. And that's where this LSTM is going to come into our model. As well as that, we're predicting Bitcoin closing prices, right? So we're only predicting one thing. So we add the special thing called a dense layer, and I've programmed units equals to 1 here because, again, we're only predicting one thing, and that one thing is the a continuous value representing the Bitcoin closing prices. Well, in our case, actually, the scaled Bitcoin closing pricing, the scaled Bitcoin closing prices, which we can then unscale later. Cool. We now do this thing in TensorFlow called compiling our model. And essentially, this is just a further step that's required to set up our model. A common metric in regression tasks, so when we're predicting a continuous value, a common metric in regression tasks is to use something called mean squared error, which is just the measure of how close your actual values are from what the model predicts. So it's just like a little metric that we can use to see how far our actual values are from what's being predicted. To actually allow this neural network to operate the way it does, we have to choose the optimizer that we want to optimize this model with. A very popular method is called Atom. We don't really need to go into the mathematical details of that. But again, for those who are more familiar with gradients and derivatives and stuff, we can use a process known as stochastic gradient descent, and you can put that in there as SGD. So for anyone familiar with a process known as stochastic gradient descent, you can put SGD in there as well. There's a whole lot of other optimizers you can put in, but if you're not sure, Atom's always a good one to start. So, just a thing to note there. With the summary, we haven't actually trained the model, so just keep that in mind. We haven't actually trained the model yet. But with this summary, we sort of get an indication of what our model looks like and the number of parameters that we're optimizing. So if you were to hypothetically go back to Gian's slides, you'll see the construction of a neural network and how there's lots of different weights and biases and all these parameters that need to be optimized. And it turns out we have 1,169 of them to optimize, which is actually quite low. this is seeing something like this is you'll often be training lots more parameters than this. That's sort of what I'm saying there. So what we can now do is fit the model to the training data. And I guess what I mean by fitting the model to the data is just telling the neural network, okay, here's our data, go learn the patterns and see if you can, fit the data in such a way that you can actually then make accurate predictions later. And so that's sort of exactly what's happening here. So TensorFlow has a special thing called model.fit. And just a reminder, model is what we set up earlier and added all these things to. So we can use model.fit, and the data that we're going to be using to fit the model is what I've called xtrain. And all that xtrain is just all of those sequences that you saw earlier from create sequences, which are then being converted to 3D arrays. Cool. Then the thing that we're actually trying to predict is our y. And we don't want to give it any access to our testing data just yet. So we're training on the training set. This batch size here, it turns out that TensorFlow is behind the scenes doing this thing called mini batch gradient descent. And what happens is the way in which neural networks learn, as I said earlier, are based off quite sophisticated calculus, in particular computing lots and lots of partial derivatives. So what happens is when we're actually computing these derivatives, a lot of the time, often we don't want to compute the derivative based off the entire data set, because sometimes our data sets can get very, very big. So computing the derivative based off our entire data set can be quite computationally expensive. So we're just going to select a few rows to do the gradient calculations. And that's what batch size is doing there. Again, if you're not familiar with calculus, don't worry about it. Verbose equals 1, that's just a way in which we can sort of restrict the output that's outputted here. We can set it equal to 0 to just shut the output off completely, or set it to a higher number if you want more output, right? Maybe from like a learning perspective, if you want to display more output, you can adjust the verbose parameter. Okay. Now, the epochs parameter here that I've just passed into model.fit is just the number of iterations that we want to cycle through our data with. And so what you're sort of seeing here is I've programmed 30 epochs here. You can program more depending on time constraints and things like that. But you see here that it's doing 30 iterations of the algorithm. And what you're going to see here is that it documents both, it documents this thing called loss, which I'll go into later with a visual. But what you're going to notice here is that the loss is more or less going down. And what that really means from a practical perspective is that our model is learning more and more from the data, like the more iterations of like doing the fit. Okay. So it's learning more and more of the patterns that exist in the data as the iterations or epochs go on. I also included this thing called validation data. You'll see what this is once I show a visual on the next little cell, but that's just something to consider as well. TensorFlow allows you to pass in this thing called validation data, which I think might be defaulted to none, but we would have to double check that. Okay. Cool. So with a bit of matplotlib/seaborn magic, we can actually plot our results from the model. And what you're seeing here is that all I've done here is just using the matplotlib.pyplot module. So you'll see in an earlier import here, we imported matplotlib.pyplot as PLT. It's just a visualization library that you can use to visualize your data. And if I scroll down a bit here, yeah. So we're creating a figure and we're creating 2 individual axes. So axis 1, axis 2. That gets placed in a tuple. So just a little Python thing there. And what we're essentially doing is on our first axis, we are plotting the training loss. So we are plotting the error that our model has been making on the training data. And you're sort of seeing here as the iterations go on. So as our model is learning more and more about the data, so too the error is decreasing, right? So as the Lstm, the Rnn model learns more about what's happening in our Bitcoin closing prices, so too is the error going down. Now, one alarming thing actually is that the validation set. So the set that's sort of been hidden away, the set that we're going to use to actually evaluate the model. It hasn't been seen by the model yet. We'll get to that later, but it hasn't been seen by the model yet. And what you're seeing here is that the loss, so the error on the unseen data, is actually going down quite a bit as well. And normally what happens is, it might go down a bit, but as your model overfits to the training data, or sort of like overreacts to the training data, the validation loss might actually go up again, but it seems to go down, almost monotonically, which might raise some alarm bells, but we'll see some of the caveats of this model in Sophia's section. And then just, here's some matplotlib, or Seaborn rather, just some Seaborn settings that you can use to customize your graph. Just one more thing, actually, you're going to notice, I know this is a RNN workshop, but I thought I had to say this. If you want to shut down this annoying output, all you have to do is just put a colon there like that. Just, something I thought I'd talk about. Cool. So that's essentially the construction of the model. What we're essentially doing there is, just to recap, really. One, we have to use our split data that was covered in Julian's section, scale it. So the data is now being scaled. And then what we do is we create these sequences. So just a reminder, we're using these first 5 values to predict this one. Then we're using the next 5 values to predict the one after that, and so on. There is a little bit of reshaping that sort of has to happen. You have to convert it into like a 3D array sort of structure before actually fitting it into TensorFlow, but it's just a pre-processing consideration. This was all part of actually constructing the model, and then it's just as simple as .fit to actually, tell the RNN, go learn the relationship and go learn the pattern of the Bitcoin closing prices. Okay. One thing I thought I'd mention just before I finish off with my section is that there is a new library called Darts. So if you weren't so much a fan of all the reshaping that had to happen and all of the creating sequences and then, reshaping the data into 3D arrays and things like that, if that was something that seemed a little bit intimidating or not something that you actually want to do, you can actually let a library handle it for you. And this library is called Darts. So it's quite a new library, and it's a very high level in the sense that you don't have to do much yourself. The library sort of takes the brunt of the work in actually doing the modeling. But essentially what we can do is it's as simple as importing something called an Rnn model, and quite literally all that you really have to do is set up this Rnn model, Lstm, and with minimal data pre-processing, you can do this model.fit. And as well as that, you can actually, as simple as model.predict, we can make predictions on future data. But that's what Sophia's going to cover, making predictions on future data. And I think I'll hand it over to her now so she can go through that.
Thank you, Noah. I will now. So after we make all those training and finally build a model, we actually have to do some inference and make predictions. So we first just want, the way we predict our training set is to pass in the data and use this predict method. And in this line here, we are actually inverse transforming the scaled y into its normal range and result in y hat, the training set prediction and the test set prediction. And we are just rescaling the training set of y and testing set y back to normal scale to plot this line plot. And as you can see in this plot, can't really know which color is which, but one is the test set and one is the original true y and one is the y hat. And looks suspiciously accurate, and we'll explain why that's the case. This is also the same for the test sets. And remember, we are predicting the closing value, so this is the original data. The few caveats from this entire procedure of training the recurrent neural network. The first is that we are assuming the data are stationary. Remember, time series data are fluctuating and it's usually unbounded. So in the first place that we normalize our data using the mean and standard deviation, we're actually assuming that the mean and variance does not change in the future as well, which is one of the caveat. Another is that there is a data leakage problem. So, which is the reason that the two, our predictions is so close to the true value. The reason is, remember when we passed, at the beginning, we passed in the previous 5 days to predict the next day, but in reality, that couldn't be the case. For example, if you want to predict into 7 days, we do not have the future 1, 2, 3, 4, 5, 6 days data. We can only use our history data to predict the first day and use the history data and our first predicted day, our first prediction to predict the second day. So in practice and intuitively, our prediction should be getting worse and more unreliable as we are predicting more into the future. Yes, and another few caveats in general for the practice of machine learning is that we should not be passing the validation or passing the test set as the validation set. So not because we only overfit on the data, we can also overfit on the hyperparameters. So that is why we shouldn't pass validation set, pass test set as the validation set. And yeah, so in conclusion, the main problem that we should be aware of that if you are doing prediction for time series data, it should be never cheat as what we did here and be careful with suspiciously accurate predictions. Yep, and I think I'll pass back to, I don't know, Julian.
Yep.
So I mean, I guess just a awesome. Yeah, so I guess just a quick thing to note there, just about actually the whole data leakage and the caveats that exist in this model. If you look here, just one point that you might want to consider. When Sophia in her section, she did, when in our section we did, model.predict x test, and then we like inverse transform to get the scaled values back to the non-scaled values. The truth is we're never going to have x test in the real world, right? Because that's the whole point of a forecast. We don't have the future data. And so that's essentially why the model is so like in quotes accurate, where in reality it's not. But that's why it's just one thing to be careful about. You see all these like YouTube tutorials and like blog posts that like, predict the stock market. And what they're really doing is not doing that at all. It's pure like data leakage. And what you'll see here is, if I just go back to darts, the way in which it's actually making a forecast is it's saying model.predict, and just notice how there's no X test here, simply because there's no data to make the forecast on. It's a pure forecast, where actually it's just like almost like a shot in the dark, like using like an educated guess in a way. And so what you'll see with darts is that you just specify the number of periods that you want to predict out into the future. And you'll see here that this is just independent of like X test, because we wouldn't actually have X test in the case of a true forecast. So just another thing to note there. And that's why you see all these like misleading, especially on platforms like YouTube and stuff. It's just something to be careful about. And for that reason, we've linked some videos here that just further explain this, especially the concept of stationarity as well. Well, that's quite an important part of time series, just generally. I think I'll head it back to now.
Cool. I think we lost you a little bit there, Noah. Can you probably repeat what you just said for more clearance.
How much of it do you guys miss?
Just like around 15 seconds.
Literally nothing. I think all it was just we put some links here that actually explain what we've explained. But this workshop's confined to like an hour. So if you wanted to actually further do some reading on this topic with the whole why these predictions were so in quotes accurate, what you can do is look at some of these links, and there's some videos that actually explain the caveats that exist in just stock price prediction models in general, and why often you can see sort of like misleading results, especially on platforms like YouTube or on blog posts that tell you that you can predict the stock market with RNNs and things like that. Yeah, but yeah, that's pretty much it. It's just addressing things like data leakage and stationary data, which is like a very important part of time series. And I think, yeah, that was about it.
Awesome. Yep. So we've reached the end of the presentation. We would like to bring it back to the room for any Q&A session if you guys have any questions, and also bring it back to Julian for a photo session.
Yeah, thanks everyone. Hope you had a good time and enjoyed that workshop. Just one lot more thing before we finish. If everyone can turn their camera on, and we'll take a quick group photo. So John, if you can stop screen sharing, it'd be great.